Okay, so today's lab is on Ohm's law and series and parallel circuits. Let me share my screen and we'll get started. Okay, so in here, same as usual, we have our instructions. This week's lab is worth 60 points. It's a bit more, you have to do a bit more than in some previous labs. Um, so be aware of that. Going into the instructions, we have at the top. Same format like normal. Remember, we always need to write our own introduction somewhere near the top, and it's roughly a paragraph. Um, okay, so same sort of format, follow the directions sort of step by step. If we go into this simulation at PhET, right here, this website, we'll get to something that looks like this. Okay, so in here, we'll be going into this intro section. That's where we'll be doing all of our experiments. And here we have on the left, we have plenty of circuit elements. So like a wire, a battery, a light bulb, resistor. On the right, we have the tools that we'll use to measure so actual values. Okay, so let's go into the instructions, see what it says to do. The very beginning, we're going to set up this very simple circuit. This is the most simple circuit. It's with a battery and a resistor. The actual sort of how it would actually look is on the left, and the circuit diagram is on the right here. So let's, before I get too into it, let me actually show what this would look like. You're going to go in and actually measure values yourself, but we have this resistor and click and drag the battery out. We have battery. Now, as it is right now, these are just two things that are sitting on my desk. They're not a part of a circuit yet. I can connect a wire. The wire is up here. And let's connect one end of the wire to one end of the resistor. Let's connect that other end, so the other dotted circle, to one end of the battery. And you can see the little dots on here, those are representing electrons. They're not flowing quite yet. So this isn't a complete circuit yet. We need to make a closed loop, and that will be a complete circuit. Let's add another wire to this other side. Now you may see that the electrons are flowing now. So this is a actual circuit that has charge flowing in it. Okay, so we have these tools on the right. Let me drag them out. So there's the voltmeter, that measures voltage, and the ammeter measures current. Thing to note on when you're measuring voltage, you have to use, so you could click and drag these probes around, you have to use both of these in order to get a measurement. So I can't just place one of them on a location. There's no reading for just a single one. I need to place both things, both probes. This is because in real life, we'll have to measure voltage across something. So commonly you'll hear, what's the voltage across the battery? That simply means what's the voltage at one end compared to the voltage at the other end. So that's why I have this one. Let's say I put this one right here, and I put the other one right here. And that's what it's doing. It's comparing those two positions. Um, does it matter which side is which? Not quite. So if I switched it, this one over here and the red one on the left, it's just going to give me a negative sign. for negative 9 volts, you can disregard that minus sign for this lab. It isn't quite important which one it is. If I switch it, that's positive. Okay, for the current, you only need this one single probe that will go wherever it tells you to place it on the circuit. Okay, back into the instructions, we have done this very simplest circuit. Okay, after this, moving down, we're going to make something that's a bit more complicated. And this is going step by step. It should instruct you fairly well. We're going to add 2 light bulbs to a circuit. And these light bulbs are going to be arranged in series with one another. So series means that, so looking at this example, the charge will flow out one end. Let's say it's going this way. It'll flow out one end, and it'll have to go through one element of the circuit. It goes through the light bulb, and then it's forced to go through the next element. It makes this one big loop. That's called a series circuit. You're going to take your tools, measure certain quantities, measure voltage, measure current in that arrangement. Going down, we're going to change that arrangement slightly. These are more measurements. Then we're going to arrange a parallel circuit. This is a arrangement where the charges can choose which direction to go once they reach this junction right here at the top. Again, measuring voltages, measuring currents, and we're going to try to figure out what kind of relationships we can see with voltage and current. Was there something happening in the series that's different than the parallel, or what? That's what we're going to find out today. Okay, so arrange it one way, and we're going to tweak it for this second set of measurements. At the very end, that's where we put all of it together. We sort of look at anything that we've seen, what sort of relationships we saw. So specifically for 4.1, it's when you get here, this is just a statement. It doesn't ask a question. What you're going to do is use your data and basically just check off to see if your data matches what this statement is saying. And you could say yes or no because of this and that. Same thing for 4.2. At the very bottom, 4.3, you can use that as your conclusion as long as you make it thorough enough to cover all of the topics. Okay, and at the very end, like always, there's this feedback section. Instead of filling it out like we have, if everyone could go to this link right here and sort of take this little like checklist. This is not graded. I don't think your name is attached to this even. So it's just to see how the instructions are written and how well or how they can be improved. This will go directly to the lab coordinator to maybe make the instructions better. Okay. Yeah, that. For today, there's a lot of measurements, and I just want to see that everyone's doing the measurements properly. So the only thing I am looking for today, the only thing I'm checking off is your measurements for this first arrangement. So right after this picture, so task 2.1, I want to see if you are able to measure these values correctly. Once I see this, I would say you're good to go. However, I'd encourage you to stick around and finish the rest, especially this parallel case, because it can get a bit tricky later on, especially trying to summarize at the end. Okay, so just checking off, up to this measurement section, this very first one. That's what I'm doing today. Are there any questions on this procedure? If there are, go ahead and shout them out. I'm going to switch to the notes right now. Okay. So today we are going over Ohm's law with series and parallel circuits. Okay. Starting out very basic. Let me first make the uh, circuit diagram sort of symbol for a battery. So we have a small plate and a large plate, and they have two little wires coming off of them, like this. Okay, you may have seen sort of an introduction to this already. Maybe you haven't. So we have a battery. We know the larger side is the positive side. Let me put positive right there. And let me do a symbol for a resistor. That's just a zigzag line with two little wires coming off of the ends of that. Okay. Typically, Okay. Typically, a battery, you buy it from a store, it's rated at a certain value. Let's say this battery is rated as 9 volts. Well, from 2 weeks ago, we learned sort of a bit about voltage or volts. That's a potential difference between charges just being in a space around a charge. There's a potential, electric potential. So when we call a battery a specific voltage, that means there's this potential difference inside of the battery. So more specifically, let me put this up higher. It's rated at 9 volts. More specifically, it means there are 9 volts worth of charge on the large plate, and there are 0 volts on the small plate. So the difference between these two, that's the potential difference. Since it's 9 minus 0, it's just called a 9-volt battery. Okay, like I said earlier, this is just a battery sitting on my desk until I connect it properly to a circuit. So I can, like our lab today, make this little dotted circle around the ends. Now this is not typical of a circuit diagram. I'm just making it obvious that I'm going to add a wire. So that line represents a wire. One end of the battery, the positive end, is connected to one end of a resistor. Since there is 9 volts of charge on this large plate, You may think they would want to flow out, go over and around, go down the wire and turn the corner, go through the resistor and escape. But that's not quite the case. The battery wouldn't necessarily do that. And this is not considered a circuit quite yet. Let me finish this circuit by making it a closed loop. Remember, circuits are always closed loops. Okay, these circles are just here to help represent wires that I'm adding. Okay, now, in the case of the circuit, the charge, we can actually even think of it as on this large plate, there are many, 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 many individual charges stocked up on that plate. And as the circuit is completed, the charges, they can tell that at the very end of this path is this potential of 0. And they could tell there's this difference. If you want to think of it as water and flowing through a tube, this large plate, you could think that's the high pressure region, and the 0 volts, that's the low pressure region. So water doesn't want to be pressurized, it wants to go to the low pressure zone. So that is why charge will flow through the circuit. And it'll go, turn the corner, round, it'll go through the resistor like that, and all the way back to the battery, the typically negative side. Okay, so what do we have here? So we have voltage and we have resistance. So R, this is the resistor R. Something to keep in mind for this is we have this one loop. I just represent that with a little symbol like that. And it's a closed loop with one resistor in it. Let me, a resistor, if you've ever seen a circuit in person, resistor in person is fairly small and looks sort of like this. So if you can see that, there are these little tiny things that you add to a circuit board, and they're all kind of the same shape. How can you how are these, different from one another when they're all kind of the same size? Last week when we were looking at resistivity and resistance, we saw that length affects resistance, cross-sectional area affects resistance, and these are all kind of the same size. These are real tiny. Well, we have to remember the object's material, the resistivity, affects the resistance also. So on here, each of these, so like looking at this example right here, these two resistors are made with slightly different material. And so they have slightly different resistivities, and ultimately they have different resistances. If you wanted to know more about this, there are color-coded. Each of these lines on here represents a value, so we don't have to actually measure it or even like print small numbers on each and every resistor. Okay, so we have a resistor R, we have a battery V. We can use, let me just jump to it. We can use Ohm's law, which states that the voltage in a circuit is equal to the current I times the resistance R. voltage, current, resistance. We already know voltage is V. We know from last week resistance is ohms, it's capital Omega. And current is measured in amperes. We call them amps. Their symbol is just A. Okay. Let's go down here. Let's make a couple circuits, a couple more difficult circuits. Let's do series and parallel. I want them to be a bit more difficult from that very simple one above. Let's make them with a battery. Say there's one battery, it's on its side. There are the wires coming off of it. There's the positive side. And I want the circuit to have 2 resistors in it. So still pretty simple, but it's more complicated than that first example. So I didn't have the dotted circles. This is more typical of what you'd see in a circuit diagram. So we have the battery, V. Let's call this first one R1. Let's call this second one R2. Now, this is a closed loop, so it is a circuit. In fact, let me put that up here. Circuits have to have closed loops. Okay, that's just something we need to remember. Okay, so looking at this series example, it's series because, like I said earlier, the charge will come out, go around, and it's forced to go through R1. Then when it's done, it's forced to go through R2, and then it's allowed to come back to the battery. Okay, and this is a one loop like this. I'll just put this symbol, so it's one loop. One loop with a battery and 2 resistors in it. Let me make a similar circuit, but that's just arranged in parallel. So positive, negative, and let's have it go through one resistor right here, like that. And in order for me to connect a second one in parallel, it has to be given, the charge has to be given a choice. So let's say the charge comes out, and let's say right when the charge gets to right here, the path is going to split. And this big dot, in fact, this big dot down here too, are called junctions. You think of it as a fork in the road, the charge can choose which path it wants to take. So since this is a fork in the road, let me make it a bit bigger. Okay, let me zoom in. Let me call this one R1. Let me call this one R2. Okay, So once the charge it's flowing out of the battery and it gets to the junction, let's say it decides to turn and go through R1. It wants to go this way. Okay, it'll go through the resistor, and once it's done, it'll get to this junction, and ultimately it's going to want to go back to the battery. That's its motivation. Okay, so we have this small closed loop right here. How many things are in this small closed loop? There's one battery and one resistor. Okay, we'll take note of that. Let's look at the other example. When the charge flows out and it gets to the junction, and let's say it doesn't want to turn here, it wants to go forward some more. It wants to go that way. Then it's going to go through R2. It's going to, after it's done, it will come out and it'll get to the junction. And once it's here, it's going to decide to go back to the battery. So now let's look at this loop. This is also a loop. It's a much bigger loop though. It's the big, I'm going to make a big arrow. It's a big outside loop. And I'm not going to keep that there. It's a bit confusing to look at. So this big outside loop, how many elements are in this big outside loop? There's one battery and there's one resistor. Okay, so I would say remember the closed loops with your circuits. That'll help with sort of summarizing in the end of the lab. Let me do since I'm already here, I want to go over just sort of adding or calculating uh, maybe some current through a circuit like this or like this. You know, if we're given Ohm's law up above, voltage is current times resistance. How do we use Ohm's law when there's two resistors? Which one do we use? How do we manage this? Say we know the voltage and we know these two resistors, the resistances. How can we find current? Well, what we have to do is lump them together, lump the two resistors together as if it's just one big resistor. So let me draw this dotted line. And I'm just, lumping them together. I'm going to say that is, I'll call that our total. Now what I'm doing right now, adding resistances, we're not going to do in the lab. I just figured I'm already here in the notes, and it might be helpful for a future lab or possibly just your lecture. So we have our total. It's, lumping these R1, R2 together. Let's write the relationship. Our total is equal to R1 plus R2 because they're in series. And this is how resistors in series behave. Okay. It's similar, but just a little bit different when looking at resistors in parallel. So let's do this. We're also going to try to, it's a bit complex. Let's try to simplify. That's what we're doing on the left. Let's try to simplify the right. So I would take all the resistors, R1 and R2, and I'd lump them together. I'd call that one big resistor. And to make it different than the one on the left, I'm going to call this R equivalent. Now the rules for adding resistors in parallel is different than in series. We need to do this when adding resistors in parallel. We need to have 1 over our equivalence. So just EQ for equivalence. That is equal to 1 over R1 plus 1 over R2. That may not seem like a big deal or even a difference, but there is a difference. Okay, so now, in the dotted regions, I've lumped the resistors together. We now have this simplified circuit. Let me draw this simplified version. So the simplified version of that series is now, voltage, battery. Now this is just one resistor. That's just one resistor in a loop that's called R total. And the same thing for the circuit on the right, the parallel. We have simplified it, so now it looks like this. Positive. Okay. And this, after we, add and then flip the fraction over at the very end, we'll get, voltage and our equivalent. And this is how we can find, currents and stuff, whatever we need. And it's just this one small loop. Now, these steps, finding resistances and all of this, we're not doing in the lab. I just figured I have the pictures up already. It's probably helpful to have. Let me do that. The only last thing that I can put in the notes, let me do this. What are Kirchhoff? C by R. C, I think it's 2 H's. O. Rules. So I'm going to have you look those up. Why look them up and not just write them right here is because I think we might be doing a whole lab on this next week. These rules probably going to help you with today's lab. I don't want to go too far into next week already, though. So be mindful of Kirchhoff's rules. Remember to check how many loops there are, or check that there are closed loops. See what's in each closed loop. Okay, I think that's it for the notes. Does anyone have any questions on the notes or the lab? All right.